Okay, so we're going to look at a topic that's, gives students a lot of trouble, and that's the formal definition of a limit. Now, this is very different from what we've been doing so far and what we're going to do. It's an abstract concept, but it's really important for everything to work properly. So I'm going to do the best that I can to explain it in a way that's intuitive and easy to follow. So here we go. So suppose that you've got a function defined for x in an open interval containing c, but not necessarily at x equal to c. Then the limit as x approaches c of f of x is equal to L if for all epsilon, this guy is called epsilon, greater than 0, there exists delta greater than 0, such that the absolute value of f of x minus L is less than epsilon as long as x minus c is less than delta. And you say, what? What are you talking about? This is some other language that I do not understand. Well, you would be absolutely correct. Okay, so let me try to break it down for you. Okay, so here's a function. Let's say we've got this guy right here. This is f of x. And let's say we're going to take a look at the limit as x approaches 0 of f of x. Now, from looking at the picture, and what we've done, you would say, oh, well, yeah, it exists, because coming from the left and coming from the right, it's the same number. But what we want to do is we want to prove that rigorously using the definition. Okay, so what's going on here is that let's say we're trying to prove that the limit as x approaches 0 of f of x is equal to 0. Okay, so what you do is, since this is sort of the thought process, it says, the definition says that for any epsilon greater than 0. So what that means is that this has to work for epsilon. Now, epsilon is typically small, so it has to work for, just like it has to work for 0.1, it has to work for 0.01, or 0.00000001. So it's an arbitrarily chosen number, but you choose it in the beginning, and then it has to work for that number. Okay, so here, let me just show you on a picture. The absolute value of f of x minus L has to be less than epsilon. Okay, so let's just pretend. So let's say that epsilon is equal to 1, and we've got L is equal to 0. Now, this guy right here, f of x minus L, or f of x minus 0, what we're saying is that we want it to be less than 1. So this is what we want right here. We want f of x minus 0 to be less than 1. Now, here, f of x minus L, this is the distance from your function to the value. So here, for example, if I want this to be less than 1, so what I'm looking for is I want it to be less than that much from here to here. Okay, now to satisfy this, I've got I'm going to call this my tool. My tool is I can make x minus c be less than delta. So this one you have complete control over. Now c here is this guy. So what I have is x minus 0 can be less than delta. Now you choose what you want delta to be. So let me just say, for example, that I pick delta to be equal to, let's say, 2. Just as an example. So if I pick delta to be equal to 2, what I'm saying is that let's call this guy the x gap. So the distance between x and my c, which is right here, 0, is equal to 2. So that means that this is my x gap. So what you've got here, what you want is, given this choice, you want the distance from the function to be, from the function to the limit, to be less than 1. Well, hey, the distance from the function to 0 right here with this choice of gap is equal to 3. This is not good enough because I want it to be less than 1. Well, what can I do? Well, why don't I, instead of doing delta equal to 2, why don't I pick delta equals to, if I want it to fall in, I want to come inside here. How about if I pick delta equals to 1? So if I pick delta to equal to 1, then my x gap is going to be a distance of 1 away. But now, check this out. When I take a look at my y gap, the gap between my function and the limit value, this guy is now less than 1. So that checks out. Okay, so that's the idea. You want to shrink the x gap so that if you shrink it enough, it fits inside of your y gap. The tricky part here, though, is that it has to work for any epsilon greater than 0. So what it is it's kind of like a little game where no matter what this epsilon is, you have to be able to use your tool, change it up to so that it fits inside. So this is super important. Delta, your choice of delta, depends, always depends on epsilon. This right here is really important. So here, for example, if this changes to let's say 1/4, that means that your y gap is no longer up here. Your y gap is now, let's say, right there. So this value, delta equals to 1, no longer works. But what you can do is just make delta smaller so that you can be inside of there again. So hopefully that process makes sense, where epsilon is chosen, and then you have to, epsilon is given, and then you have to choose your delta, your x gap, so that it fits inside of the y gap. Alright, so I want to show you how, when it's discontinuous, the definition doesn't work. So remember that the idea is that you want to make the y gap small, and you should always be able to make it smaller. So, but notice that here, so like here, if you take a look at the x gap, let's just say we go right here, notice that the y gap is going to be from here to here. But no matter how close you get, you can get closer to C. You can get super close. But notice that your y gap is always going to be, you made it a little smaller, this much smaller. But because there's this big, huge hole here, no matter how close you get, on one side it's going to be down here. On the other side, it's still going to be up here. So you can never make it smaller than somewhere around this. So if you want your gap to be this small, for example, there's no way you can get that to happen by making the x gap smaller.